session today is about computing for all. And obviously it has intersections with the last panel and the panels earlier. And the way I interpret it is to mean teach computer science very broadly across disciplines, across different stages of education, and across geographies. So, well, I guess I forgot to tell you who I am. It's not that important, but Dimitris Bertsimas, I have been a professor here for 30 plus years, and particularly excited about this important time at MIT. The last time I think MIT had a new school or college was, I think, 1951, the Sloan School. So this doesn't happen every day, so 80 years later is something to celebrate and reflect. So we have a panel of very distinguished educators and researchers. I will focus on the education aspect, given the day. So I will introduce every panelist separately. Our first panelist is Professor Anant Agarwal, who has been a professor at MIT for even longer than I have, not by a lot. And he's the CEO of EDX. In learning about him, here's a remarkable something I discovered, is that Anant taught the very first EDX course on circuits and electronics from MIT, which drew 155,000 students from 162 countries. I would say he's well qualified to talk about geographies and so forth. Anant?
How many computer scientists does it take to change a light bulb? Okay, so thank you. Really delighted to chat with you today and brainstorm a bit about how we can increase access to computer science. But what is the problem here? To give you a quick idea of the problem we're trying to solve, there are 1.4 million CS-related jobs available by 2020. And we are producing a pitiful 400,000. Okay, so we are off by a mere factor of 4. At the same time, we don't have place in our classrooms to hold students. The New York Times article that you see a picture of here talks about how in all the classes in computer science, people could not get into those classes. And I was talking to my dear friend Regina Barzilay, and she was telling me that in her machine learning computer science class at MIT, there were so many students in the classroom, it was over full, that the police were called in. And they had to take the students out because they refused to leave our classroom. Okay? This is what is happening. And this is not a third world country where people are fighting for scraps of rice. These are people fighting for bits of knowledge in computer science. And here's the challenge. On campus, our campuses simply cannot teach the number of people we want to teach. And these numbers are true everywhere. University of Texas at Austin just launched a online master's degree on edX for $10,000. And they gave us these numbers. 1,300 students apply for their master's in computer science on campus. They make 100 offers, and 30 people come to campus. 3%. I mean, this is insane. When everybody around the world can go in and type a search, I don't need to have a library in my house. I can go and type search. Digital technology has solved so many problems for us where we all have ample access, but we've not been able to solve one of the fundamental accesses of education. And not many people would argue that education is a human right. But then we have this gatekeeper somehow, physical space in classrooms that do not allow us to teach as many people as we want to teach. So one solution is digital education, particularly modular digital education. And let me talk a little bit about it. Digital computer science learning can scale. So on edX.org, as an example, edX was is a nonprofit founded by Harvard and MIT, where about 140 institutions, many of them represented here, like Georgia Tech and others, offer courses to people from Cornell and others from people all over the world. And we have 800 plus computer science courses, and 8 million unique learners from all over the world taking these computer science courses. And in case you're wondering, are they really completing them? Yes. 250,000 students, just in the space of about 6 years, have earned 250,000 certificates in computer science courses. So it is possible to teach computer science at scale. We can teach at the high school level. We have a number of high school courses on edX, a number of them high school AP courses. Harvard has a course on AP Computer Science Principles. Berkeley has a course on Beauty and Joy of Computing, and Trinity on, is Hal Abelson here? So Hal Abelson, MIT and part-time at Google, done some amazing work in creating the App Inventor, a way to teach computer science and build applications for mobile. Trinity College has an amazing course on edX, and Purdue as well. And so we have 1.5 million unique high school learners enrolled taking these high school level courses in computer science on our platform. MIT is doing an amazing job, have 90 plus courses on edX with 1.7 million learners on our platform. And here I'm broadly construing it as a data science, computer science, and related courses with the 25,000 certificates earned. And Eric Grimson, who's sitting here, probably single-handedly contributed to a large fraction of them. Eric and John Gutag teach the MIT Introduction to Computer Science and Python on edX. And what I want to stress here is not only is it a free course, and people are earning certificates, but this is accessible in the ADA sense. You see this learner here, Bhargav. He's from IIT Madras in India. Someone want to guess what's unique about him? He completed this MITx Grimson's computer science course on edX. And this is the same as 6000 at MIT. And he completed this course. Anyone want to guess what's special about him? He's blind. So the platform is WCAG 2.0 AA compliant. The World Wide Web Consortium that has the WCAG 2 standard, they themselves have courses on edX. They're housed in CSAIL, front-end web developer. And here's another student, Larissa, who's completed their program on edX. Online courses can also help meet campus demand. I mean, isn't it insane that we're not using digital technology to solve the problem that involves teaching digital technology? It's a bit, a meta-circular. We all remember meta-circular evaluation and scheme and stuff, and so we should be using the technology we create to solve the problems of the same technologies. So Georgia Tech, a couple of my Georgia Tech colleagues or friends are here. So what is Georgia Tech doing? The enrollments in the Introduction to Computer Science course at Georgia Tech was overflowing. So what they did was they allowed their students to take the fully online course on edX, 100% online, or they can take the campus course. And our friend Zui Galil, who's the dean there, tells me that 82% of them rate the online course as better than the campus course. And today, 60% of Georgia Tech students are self-selecting into the fully online course. MIT has done the same thing, although MIT did it with a circuits course. So MIT had a circuits course where half the students took it online, 100% online, not blended model, 100% online, and half took it on campus. And this was an experiment. And they even gave the students the same exam. And the research paper was written by Ann Marshall on the study that talked about how the results for the exams were pretty similar. So online courses have come of age. Universities like Georgia Tech and MIT are giving campus students credit for completely online courses. In addition to access, so far I've talked about access and how we can use these courses to solve sort of a major access problem. How do more people learn computer science at the high school level, at the college level, and also how do we solve the problem that we face in colleges that our classrooms are simply not big enough. Regina just told me that she had to cut down the enrollments in the class to 90 because MIT did not have a classroom big enough to hold the number of people she wanted to hold. This is insane, folks. I mean, this is nuts. I mean, can you imagine real estate? I guess Cambridge real estate is a different thing, so there's a real constraint. I know the rents we are paying at edX. The other important thing is that there's another major challenge in the world, which is this upskilling challenge, where various studies have shown that within the next 10 years, half of today's jobs will have to change in one way or the other. People will have to learn radical new skills or lose their job. because of automation and AI and all of the things that Regina and company are doing. It's all your fault. And so, the whole planet has to upskill. We all have to upskill. And how do we get these skills out to people? How do we train people? How do they learn? Many of them are working in companies. Many of them looking for jobs. No way they're going to come to a campus to get a master's degree or a second bachelor's. No way on earth. Nor do they have the time to learn online and do full one-year masters or multi-year programs. We need modular credentials. We need modular approaches to teach people. And the first picture I showed you with those Lego blocks, it has the answer, which is we need modular education. And at edX, a number of modular programs. MIT pioneered a new modular program called MicroMasters. See, masters, micromasters. Computers, microcomputers. So the MicroMasters are 1 year long or 2 year long. MicroMasters are about 25% of a master's degree and fully online. And people can take these and complete them and get campus credit if they get admission into the university. So you can get a MicroMasters in MIT, from MIT, for example, in data science for about $1,000 today. You can also do radical, crazy things with modular programs. You can stack. To my knowledge, it's the world's first stacked multi-institutional degree. So MIT has a MicroMasters program in supply chain management on edX. So Arizona State, MIT is the #2 ranked program in supply chain. Arizona State is the #3 ranked. They said, hey, why do we need to create a full master's degree? Let's take MIT's MicroMasters. Let's just create the complementary part. MIT has 4 courses. They built the 6 courses, and they launched a master's in supply chain management on edX, modular. So education will become like Legos. It will go online. Campuses will have online learning and campus physical learning at the same time. And I see a world in the future where this kind of modular digital learning can really address the kind of needs that our planet faces in computer science and other, frankly, other technologies. Thank you.
Our second panelist is Professor Regina Barzilay from our computer science department here. In addition to being a recent winner of the MacArthur Award for her work of developing machine learning methods that enable computers to process and analyze vast amounts of human language data, she's a recent recipient of the Jameson Teaching Award, one of the major prizes of the Institute for Teaching. Regina?
Thank you very much. I learned that there are actually many other recipients here on the panel. Okay, let me start. I'm not sure. What am I supposed to be doing? Oh, to where? Huh?
Suddenly 6 slides will advance, so watch out. Try it again.
Yeah. Okay. I arrived to MIT in 2003. And when I arrived to MIT in 2003, AI was not a popular term, and we didn't have like hundreds of students who wanted to get into the classes. And at the time, machine learning classes were taught all on graduate level. So there was no question, teaching non-major machine learning. We barely had, majors who were studying it and majors which were graduate students. So clearly, the situation changed, and if you don't need to go far, you can just open a newspaper and you would see that, AI and machine learning does all different types of miracles across all different disciplines. And, our students read newspapers, and of course, their interest in machine learning greatly increased. So around maybe 6 years ago, Tommy Yakola, who is a professor here, and myself, we thought we actually have to start teaching this class in the undergraduate level. And that's how 6036, one of the very popular classes in machine learning, was born. And you can see for the few years when I was teaching it that the enrollment steadily increased in this class. And originally we taught it just once a year. Now we're teaching it twice a year. But what I want to tell you that there is something else that happened. What we noticed is that as we continue teaching the class, the composition of the class greatly changed. Originally, this class was designed for non-major computer scientists. And you can see in 2013, 83% of the students were in computer science. If we are looking at the chart in 2017, you can see that almost half of the students in the class actually non-majors. And they cover almost all the different majors across MIT. They're not computer scientists. And this was a great news, correct? Because we really can see, with one class, we can deliver the goods for the whole community. However, the part that you cannot really see on this chart is what happens to non-major when they take this class. First of all, they have much higher rate of and chance of dropping from the class. And second, their grades are much lower than our majors. So the question is, if you still want the students to take these classes and to benefit, what do you want to do? So one answer, which is really unsatisfactory answer, is to say, you know what, we're going to do a remedial class. We're going to take a normal machine learning class, water it down, and make it for non-majors so that they can succeed. And you can say now the landscape of research totally changed. Now we have all these big building blocks. We have all these different machine learning packages, which are very high level. So maybe we can just teach them how to use these packages, and that's it. So I think it's a wrong approach. What we really need to do is to enable people who are users of machine learning technology, future users of machine learning technology, really to think about modeling. What are the problem formulation strategies? What kind of tools you can solve? You can use to solve it. Now let's just look at the curriculum of standard machine learning class that we are teaching, that everybody are teaching. It's there are variation of this class. So what you would see here, the cross like lectures that I put on my slide, the vast majority of it is classification. So for those of you who are non-majors and didn't take machine learning class, there is one technology, which is pretty powerful technology, just one building block. And we're looking at different ways to build this block inside. We're not talking about what are beautiful things that you can build from these things. How do you need to select the right type of blocks? We're just focusing on one technology. And to me, one of the biggest surprises working with MIT undergraduates who are majors, who did very well in the class, that even they don't understand how to put these blocks together, how to decide which of this technology can be useful and how to move forward. So the topics that are really absent, which are really crucial for using machine learning technology across disciplines are, kind of core pieces of technology like making the models interpretable. If your models make a prediction and you're using it in healthcare, you're using it in financial industry, how can you explain what is it doing? And it's particularly a problem when we're thinking about deep learning models. We don't teach it. Another big question, which is a very useful question, what do you do when you are training your model on one type of data and you need to apply it to another type of data? Very, very common scenario across disciplines. We don't talk about it. Another one is sparse data. For the vast majority of applications, we don't have huge data sets. What tools do we give to students to address these questions? And of course, there are all the different kind of scientific paradigms that people are thinking about and talk about science, like causality and others. They are not addressed in our classes. And even when we are thinking about evaluation, when we want to make sure that the student and the user understands how you actually are using technologies, doing the right thing, we don't have any material. And there are lots and lots of kind of omissions that are in our standard curriculum. So what we've done, I stopped teaching 6036, and we started teaching a new class. I just came from teaching the class with 90 people that we have in the classroom. It's called Modeling with Machine Learning from Algorithms to Applications. And the idea is really to defocus from classification. We do teach, a few classification algorithms so the students understand what are they doing, but really to focus on the idea, how do you build from it? What do you need to be understanding and thinking when you are applying and creating new formulations? And the topics that I just showed you on the previous slides are really developed in this class. Another point that is important is the teaching style. What we realize that when you're talking about non-majors, you're looking at a huge diverse audience. You have people who are math major, physics majors, who are much more advanced than others in terms of linear algebra and probability. You have people from other disciplines. I wouldn't name them, but which maybe need more help. The approach it's from that other college, you know, that was created before Computer Science College. The point that I was trying to make, we realized that, you know, teaching the lecture, teaching the material, the core techniques in the class is a bad idea, because for some it's really easy, for some it's really hard. So we kind of recorded technical lectures, and the students can go using MITx. Students can, you know, go listen to lectures. They have exercises which they can solve. And then we're using the classroom time really to make the discussion and to think about different application scenarios. And the biggest surprise to me that actually the class that we are teaching, we advertise it for non-majors. 80% of students in this class are majors, are core 6 majors. But you know what was a surprise to me? That these majors, many of them took 603.6. They know kind of basic algorithm. I was surprised to the extent that they cannot understand how to apply them. And why do you select technique A versus technique B? So I think that it's useful both for majors and non-majors. And through these discussions, we're actually kind of learning how to move forward. And finally, we're really focusing on connecting to other disciplines like chemistry, biology, linguistics, and what we're expecting moving forward, that we're going to create specific sections for the sub-disciplines so that the faculty, part of our new college, can help them, you know, to do modeling which is specific to their area of study. Thank you.
Our third panelist is Professor Marie desJardins. She's the inaugural dean of the College of Organizational, Computational, and Information Science at Simmons University. She has done extensive research in artificial intelligence and computer science education, as well. She's well known for her leadership in broadening participation in computing. I know also, having talked to her, she's particularly passionate about K-12 education, and I think she will be talking to us about this matter now.
Yeah, so I'm sorry I wasn't here this morning to hear Tony DeRose say that he was the only one who was, I don't even know who that is, the only one talking about K-12 computer science education, but me too. I think it's really important, and I think it's essential, actually, and I'm going to talk about why I think that. So I'm not going to talk so much about the content of computer science or what we should teach to K-12 students, although I think that's really, really important to be thinking about. But I want to talk about how we could get to this place where K-12 students are actually being exposed to computer science throughout their education. And to do this, as I think was mentioned earlier today, is very challenging in the United States because we have a very distributed educational system. And what that means is that every single state has to develop its own solution for computer science in the curriculum. And in some states, every single school district has to do that. So it's really, really a challenge, and it's really about leading transformational change and how you get people to work together to really change a system that's kind of entrenched in a current way of thinking. And why do I think this is so important? I think this is so important because if we want to change the face of computing, if we actually want to have gender representation, racial representation, socioeconomic representation that reflects our society, we have to get different kinds of people into the field. And the best way to do that is to expose those people who are not currently coming into computing to computer science early in a way that lets them think of themselves as computer scientists, because they're not seeing the role models out there because they don't exist. So we have to solve this chicken and egg problem. And I've become really convinced that we have to do this by starting early as elementary school, in changing the way that young people think about what does a computer scientist look like and what do they do. So I just want to talk about what we did in the state of Maryland to address this problem. And it's kind of, looking back on it, it was a 5-step procedure that makes it sound like we knew what we were doing, but we really didn't know what we were doing until we got to the end and we said, whoa, that worked. So I want to talk about what worked and how we fumbled our way to something that I think was really successful that can be leveraged to develop similar solutions in other states. So I kind of have this 5-step thing: identify the problem, gather momentum, garner resources, solidify infrastructure, and build for the future. And so I'm going to talk about each of those a little bit with a few lessons learned along the way. So first, identify the problem. It's easy to say, oh, we need more students in K-12 computer science education, and that's a very abstract goal. But to actually understand how to do that, you have to gather more data about what the current situation is in order to address it. Like, what are the nuances of what's happening in your local region, in the schools? Who are your teachers? Who are your students? What's the curriculum? What's the state? So how did this work in Maryland? Well, in summer of 2011, I got some funding from Google through a program called CS4 to run a summer workshop for high school teachers. And we were doing this because we wanted to get more women into our undergraduate degree program. And we thought, well, where would we go to get more women? High schools, that's where the students are. So let's go to high schools. Well, who should we go to in high schools? How about computer science teachers? Who are the computer science teachers? We don't know. We don't know. It turns out part of the reason we don't know is because computer science in most schools, at least in Maryland and most states, is not its own department. Who's teaching computer science? Math teachers, maybe science teachers, maybe a gym teacher here and there, social studies, whoever we can find. And especially in 2011, that was the case. So we brought about a dozen teachers together at this summer workshop, and they were so excited to meet each other that we wanted to keep that momentum going, and that was kind of the big beginning of this whole 7-year-long process. And we started to try to keep it going, to create some infrastructure. We decided to start a local chapter of the the Computer Science Teachers Association, which is the National Professional Association for Computer Science K-12 teachers. And we're like, how do we do that? I don't know, let's pull up the website, and we have to do an application, we'll make an application. So we just did it. We didn't know what we were doing, we just thought that might be a good way to get started. And then a group of us kind of got together, we're doing some activities over the course of that year, and decided to try to get some money to do more. We ended up with a planning grant from NSF's Computing for the 21st Century program and did a landscape survey. So that got us to the place where we understood what we were facing and we could start to think about solutions. So that's the first lesson. Jumping ahead a little more quickly because I see my time. We got used some of that money to start bringing people together. So we had a couple of statewide summits, and we got people talking about the challenges and the problems and the gaps. And the thing that I realized was we don't know what we're trying to do. I mean, we know it's like writing a PhD dissertation. We know we're trying to write a PhD dissertation, but what are the steps along the way to that? You have to break it down into pieces, and especially when you're doing something collaborative, you have to find a starting point that you can get a lot of momentum behind. And a lot of people wanted to say, let's require computer science for everybody in high school. And that was a really daunting challenge. We didn't think we would get there very soon. So we started talking about what could we do that everybody in this room, 120 people at the summit, can agree is possible and important. And the goal that we came up with was every Maryland public high school should offer a high quality, rigorous, college preparatory computer science class. Everybody agreed that that was a step along the way to the big thing that we all wanted to do. And so we spent the next 5 years focusing on how do we do that. So you have to have a shared goal to bring people together, and you can't just take your goal and make it everybody else's goal, because that's not how people work. So resources. Now we've got this goal. What do? You get money. So we wrote another grant to NSF under their CS10K program, Jan Cooney's program that was mentioned earlier, to develop an AP Computer Science Principles curriculum and train teachers to teach it. So we now have a curriculum called CS Matters, which is one of the College Board endorsed curricula for computer science principles. Now there's lots out there. And we led a collaborative curriculum development process, so teachers were actually working together to write the curriculum, which I think was a really good way to do it. And we started training teachers. And doing that work together created a really strong team. And that's what kind of let us launch into the next phase. Along the way, we also started thinking about who were our partners, and we developed some really close contacts at the Maryland State Department of Education. I will say we also had people who were not as supportive, but we found the people there who were supportive, one of whom eventually became interim state superintendent. and essentially signed an executive order saying computer science can count for the state technology education requirement, which the hard part to believe is that previously computer science didn't count for the computer science technology education requirement. So there was a tech ed graduation requirement that didn't have any computer science in it. So that was a big barrier, because it's like, well, we've already got technology. We don't need more technology. Well, we do. We need different technology. And we found it was not going to work to go through the legislation, which is how that requirement had been put into place, but we could do this end run to just add another option for students. Well, the students really wanted to take computer science, because by this time, computer science was starting to explode in interest, and so a lot of factors came together to make this all work. But we had this grassroots effort, but the reason that things really came together and took off in Maryland is because we also laid down roots. We didn't just kind of get people together and talk, but we found the key thought leaders and the people who controlled resources who we could get on our side and start to think about bigger change. So the last step, and this is really exciting because I left UMBC last year to move to Boston to become this new dean at Simmons University, which is a great opportunity, but I was really worried that when I walked away, everything was going to fall apart with CS education in Maryland, because we didn't have any infrastructure. We just had some people who were working together, and I was kind of at the hub of all of it, and I thought, well, if you pull out the hub of a wheel, it doesn't keep rolling very well. So I spent the last couple of years really thinking about building infrastructure, and we established the Maryland Center for Computing Education, which originally was a cubicle and a sign on the wall. Like, it had 0 resources, but USM agreed we could have a thing, and they wrote a memo saying there's a thing. And then we went to the state legislature and we said, well, you should really give people lots of money for computer science education and train teachers and all of that, and we think you should give it to this center, because the center that's its mission. And so it all kind of was like smoke and mirrors that coalesced into $5 million in state funding in this fiscal year's budget for teacher preparation and advocacy through the Maryland Center for Computing Education. So that's how things happen. And the people who were involved in it are now the leaders of that. So the one last thing I want to just put a plug in is, if anybody is in Massachusetts and is interested in getting involved with a nascent CS4 Massachusetts activity, please reach out to me. I'd be happy to put you in touch with that group, and I think Massachusetts should be at the forefront of this, and they're not. So maybe the MIT Schwarzman College of Computing could also help with that. So thank you.
So our fourth panelist is Professor Eric Grimson, who is MIT's Chancellor of Academic Achievement and also a Professor of Medical Engineering at MIT. You heard about Eric's and John Gutak's class from Anant, how successful he was. Eric has taught more than 10,000 MIT undergraduates and has served on the thesis as a thesis supervisor for about 50 MIT PhDs. He's also the recipient of the Bose Award for Excellence in Teaching in the School of Engineering, which I understand is the highest award for teaching at the School of Engineering. Eric?
So I'm going to describe experiences, lessons learned from teaching MIT's introductory CS course. It's a class created by John Gutak. I gave him a little help. John, Annabelle, and I continue to teach it. I'm here because John's actually across campus in lecture right now doing the right thing, teaching undergraduates, and I'm talking to you. To set the context, it's a subject that's taken typically by about 900 students a year. An undergraduate class at MIT is about 1,100 students, so almost all students take it. It's a class intended for students who know very little or have very little or no prior experience in computing. And interestingly, to a point that I think Jeanette raised earlier, that number is dropping because we're seeing more students coming in prepared, and those students who come in prepared take an advanced standing exam and get credit and simply move on. The class started out as a one-term class. We recently split it into 2 halves. The first half focuses on computational thinking, and the second half talks about data analysis and computational experiments, and I'll say a little bit about that in a second. We also provide 2 online versions. We have put up 2 postings of the course on OpenCourseWare, one in, as it says there, in 2008, one in 2016. The first lecture has been viewed 4.3 million times, which is a frightening thought that that many people have heard my bad jokes. And we, as you know, we taught the second MIT MOOC. Anant did the first one. We have a course that came up in 2012 on edX. It's been offered 17 times and has had 1.2 million registrants around the world. Also a frightening thought. So, goals of the course. As I said, it's intended for students with little or no prior experience in computation. We, in fact, actively discourage students who have experience from taking the class. We don't want them to intimidate people in the class. And I'm going to borrow from 2 great colleagues before me. One of the goals is really, while the students do learn a programming language, in this case Python, the goal is to focus on computational thinking. Thank you, Jeanette, for creating that term. At least I credit you with creating that term. Computational thinking, computational methods, not the specifics of programming. This is not a programming class. It's how to problem solve, how to think a little bit like a computer scientist. And that's what we want to do, is change the student's way of thinking. And then I'm going to borrow a comment from Maria Klawe, because in addition to focusing on algorithmic approaches to problems, we want to show students examples in other disciplines. So in our problem sets, in our lecture examples, we heavily borrow from biology, physics, urban planning, economics, whatever we can. Let them see things in context. We think that really helps them think about what they want to do. So the primary objectives to 30,000-foot view are very simple. We want students to learn approaches for decomposing problems into logical steps. We then want them to learn standard approaches for converting those decompositions into algorithms. And finally, we want them then to convert those algorithmic descriptions into actual programs, especially understanding how to make efficient implementations. But notice we start with the high-level view of this. How do we get them to think computationally? You can read this. I'm not going to go through it. We use basically the things you would expect, the standard tools of any good introductory computer science class. But I'll highlight that in addition to abstraction and modularity, which are in every good intro class, we really talk a little bit more about recursive thinking and how you can use that to design algorithmic solutions in a wide range of areas. We want students, whenever they see a new problem, to say, how can I break this down into a simpler version of the same problem? How do I approach it algorithmically? I want to talk briefly about the campus version and then the online version. On campus, we mix online methods with traditional methods. During lecture, we'll take stops and we'll do what we call finger exercises. A short little question that the students do online, we look at the responses. We also assign those finger exercises during the week as well as weekly problem sets. And a big factor for us is to have those problem sets initially graded automatically by an online tutor. Our experience is that instant feedback is really valuable. I know we got lots of computer scientists here. Looking for that missing closed paren is totally annoying. And the fact that your code doesn't run is irrelevant. Instant feedback helps students very quickly identify when they don't know something and go back and look at the text. So we use that a lot. But in addition to that, we also require students to come to an office hour with an undergraduate or graduate TA and explain what they did. So they have to get a checkoff where they have to talk about why did they make those decisions, where did those solutions come from. A little bit to catch the people that are getting too much help from others, and a little bit to actually get them to explain it. One of the things I want to do, I want to talk very briefly, because I've still got a few minutes here, about the young woman in the middle, because in addition to them hearing John or I tell bad jokes, they go to tutorials. And that's taught by graduate students. It's a great thing to do. But the young woman in that middle image is, I think, a great story. She took this class many years ago as a freshwoman, convinced that she hated computer science, because her father was an MIT alum and he was a senior person at IBM, absolutely convinced she was not going to be a computer scientist, took the class, discovered she loved computer science, finished a major in computer science, became one of our best TAs. We actually have recorded her on video, which is what you see here, going through tutorials. And today, she's the chief of staff to Drew Houston at Dropbox. So, you can discover that computer science is a cool thing to do. In addition to on campus, we do have an online version, and we offer it through but as I said, OCW, which is really a static snapshot of the course, and more importantly, a dynamic version on, thank you, Anant, the great platform edX. We break the lectures into 8-minute chunks. We separate them with what we call finger exercises. Very quick question that gives you a sense of, did I understand what was in that chunk? If not, I go back and look at it again. The one difference we use here is we do not have, no matter how many times I've begged Raphael, the budget to staff this. And so we use what we call community TAs. It's an interesting experience, which I'm guessing other people on edX do. These are people who've taken the course in the past. They volunteer to serve as online TAs, and they do it purely for the glory, no money. And they will do it multiple times. We've had community TAs who've done it 8 or 10 different times, and it really helps the students get a sense of how to ask their questions. I want to give you one quote from a student who took this class. Sent me a note a couple of weeks ago. She said, quote, "Your course has really changed my life. I have a degree in civil engineering, but was having trouble finding work in that field where I am," which happened to be the state of Utah. "And I ended up as a program manager for software developers for a few years. I decided I wanted to pick up development, and your course is where I ended up from a recommendation I found online. I finished it in April, and with no further education was hired into a back-end Python development internship in May, and just converted that internship into a full-time position as of Monday. It was largely thanks to the knowledge I gained in your course, a real life changer." Now, I'm sure I'm going to get nasty messages from people who didn't like my class, but it is nice to hear that somebody can take one class and discover that they've got a way to go. So the take-home message. We want to expose students without prior experience to computational thinking. Some will go on to be CS majors. We're leveling the playing field, and that's important. But many of them will use that computational thinking in other domains. And thus, we want students to learn how to think computationally, design systems that leverage modularity and abstraction, use them to complement theoretical explorations and physical experiments with computational analysis and exploration. But we also believe that exposure to computational thinking provides a different mode of communication. You talk differently when you're thinking algorithmically. And as President Reif has said, we think every student here should be bilingual, speak computation, and something else. And this course, for many students, is a first step in that direction. Thanks.
Our fifth panelist is Dr. Jim Kouros, who is currently the Assistant Director in the Computer and Information Science and Engineering at the National Science Foundation, on leave from the University of Massachusetts at Amherst. He himself also has multiple awards in teaching. In fact, it was difficult to find what to say. So he's a 9-time recipient of the Outstanding Teacher Award from the National Technical University, and the recipient of the Outstanding Teacher Award from the College of Natural Science and Mathematics at the University of Massachusetts, among many others. Thank you.
So, thanks very much. I noticed you counted that introduction against my time. I guess that's okay. It's always...
It could have been much longer.
It's always tough being the last speaker of the day, but I'm so pleased to be here. And I wanted to start by congratulating you all. And those congratulations come not just from me, but everybody in the SCIES Directorate at the National Science Foundation. And when I was running out last night to catch the plane, France Cordova, our director, knew I was coming. She said, "Make sure you say congratulations from me too." So congratulations from all of us. I mean, what you're launching here is really historic. And actually, I want to come back to that at the end. So one of the things about being the last speaker is a lot of people have said things that you wanted to say. And in fact, is Rob here? Rob had my slide. I saw one of his slides. I'm like, I've got that slide, Rob. But what I want to talk about are really three things, and then I want to end up with some high-level just comments here. This is probably the only place I can go and say there's an interesting right-hand rule here. But I want to talk about computer science for all, what we call Q, computing in undergraduate education and broadening participation in computing. And I'm going to focus a little bit more on the programmatics from the NSF side, but Jeanette's already done some of the background for that, so I actually, I can go through that pretty quickly. Sorry. Seems like everybody's having trouble with the clicker. Okay. Wow, no. Oh, man. seems like everybody's better than me, too. Can we try again? Okay. All right, I'll just go on with my talk. I'll just talk to the slides, okay? Well, this is actually not how the right-hand rule works here, but I'll start with broadening participation in computing. We've talked about that some, about equity and access for all. The BPC alliances were actually launched at the National Science Foundation in 2007. People have mentioned Jan Cuny's name multiple times. It turns out that's when she came. Peter Freeman, Jeanette Farnham-Jahanian, who was the AD between, assistant director between Jeanette and myself, we've all supported this tremendously. I will only point out that also in 2017, we're launching a pilot where we're asking, we want this to be part of the entire community's responsibility, broadening participation in computing. We have a Dear Colleague letter and a pilot where we're requiring our PIs to do something meaningful, right? And there's a lot of background there, but we want to, it's really part of the whole community. It's something that's been part of the strategic plan for SISE for quite a long time. Okay, so I really wanted to start with computer science for all, and I want to go on record as being the fourth person now to talk about computer science education and education broadly at the K through 12 level. So as you've heard before, the idea is to enable all students. This is about equity and access. All students to have access to a high quality educational experience in computer science in K through 12, developing the knowledge base, developing the capacity, as Marie said, for teaching that rigorously. That also includes teacher professional development. NSF committed in 2016. Where's Randy? So working with OSTP and the Department of Education and nonprofits, putting in $120 million over 5 years to actually build this. And so I feel like this is a home run. It's a home run already. I feel coming in, I joined NSF in 2015, so I was born on third base as far as this is concerned, right? That again, starting in 2010, I think Marie mentioned CS10K, right? And so that was a project that actually Jan Cuny and others started in 2010 to bring computer science to 10,000 students by 2016. 10,000 teachers, right? We didn't quite make it, but we actually came pretty close, and you know, CS4All sort of grew out of that. And as has been mentioned before, one of the things, two things actually, in CS4All computer science principles and also exploring computer science. CSP is it's the second AP exam. It does not replace the programming AP exam. You see the big ideas there. Programming's part of it, but just a small part of it. It's all the computational thinking that we've been talking about before. It's about creativity. It's about the use and application of computing and computational thinking and data and algorithms instantiated through programs. Okay, so you know, the challenge we faced was, how do we scale this? And you know, Jeanette gave an example of school districts. I live in Massachusetts, in Northampton. We have 404 school districts in Massachusetts, right? I spent 2 years when I was an assistant professor working with the Northampton school system to try to get computer science into, you know, helping a math teacher there, as it turns out, getting it in. You can't do that, right? There are just too many school districts everywhere. So how do you scale really good ideas to make a national, move the needle nationally? And this was done through the introduction of this new computer science principles exam. So to me, that was just like, that's the light bulb that went off in Jan's or somebody's head, you know, circa 2011, 12. Okay, so I just want to show you some data. Everybody seems to love data. So this is data from the AP Computer Science exam, and I want to talk here about diversity, right? So what you see in the three graphs as a function of time, the number of female students who are taking an AP Computer Science exam from, what does that start, 2007 to 2018, the number of Black and African American students in the top right-hand corner, and in the bottom right-hand corner, the number of Hispanic and Latinx students who are taking that. So to me, this is a real home run and a really good thing for the community, and people have been working on this for 10 years, and I think we've got a lot to be proud of, and it's going on. The little table over there, just in terms of the raw numbers going up, you see in the graphs, but seeing the percentages changing in the number of women and underrepresented minorities taking the an AP exam there also. Okay, so Jeanette actually was kind. She put up a whole bunch of size solicitations, so I'm only going to put one up here, the one you missed, Jeanette, because it only came out 2 weeks ago, okay? And that's okay. And this is, all I want to say, this is about well, it's not just about, let me show you. There's 2 quotes from the solicitation here. This is about rethinking the role and the positioning of computer science education. There's something about X plus CS. We don't put CS first anymore. I'm just telling you that when we talk about that. But really thinking more broadly about a holistic restructuring of interdisciplinary degree pathways, right? And so I think proposals are due June 9th. So if you're from an institution that's thinking about things like computing in undergraduate education, I want to say this was built for you with exactly the kind of things in mind that we're talking about here at this workshop. Okay, so I'm going to finish up. This is my last slide. This is the slide you saw Rob put up. Although he had Illinois data there, and I have Talby's survey data there for the number of computer science, computer engineering, and informatics students who are taking classes, newly enrolled majors as a function of time. So somebody, I think Maria mentioned the snowbird meeting. This was a meme picture, the tsunami of students that were about to come in 2014, and actually, of course, it's come to happen. So it's not news that we see this increase in students. I guess the other thing, and Rob didn't have this on his slide, so I want to talk about this some, we're seeing multiple tsunamis. And actually, this gets to Greg Morissette's question, right? So yeah, we're seeing all these students come in, but we're also seeing students come in now, I think because of some of the AP exams that we've been doing, and we're seeing students come in and knowing and having broader interest in the application of computing. And so the question is, how are we going to respond to that? And I think that's going to be our challenge. And when we think about the diversity of students, we talked about gender, we talked about interests. We should also think about age, we should think about background, we should think about preparation. If maybe since I get to have the very last say here, I'll go back to Farnham's talk at the very beginning. Nothing is going to be more important over the next 30 or 40, 10, 20, 30, 40 years than education in a technologically disruptive time. That's what Farnham was talking about, right? So it's our responsibility as a community to take the lead there. Now, you're starting a new college here. You've got an opportunity here, right? Who are your students? Who are you designing curriculum from? What's the model? Is it students who are 18 to 22 are going to be on campus? You got to do that, right? But what about lifelong learning for students? What about students from diverse backgrounds? What about students with diverse interests? What is this college going to do? I'll just throw that out as a question. What is this college going to do about this? Because there's a very small handful of colleges in this country or in this world that people look to for intellectual leadership in education, right? And people have mentioned the thread models, so I'll give a shout out. I don't see Charles here anymore, but I'll give a shout out to Georgia Tech for the thread models. I think that really moved the needle in computer science, right? And we've got the opportunity, we've got the need to do that now. So I want to say congratulations to all of you, right? It's like when I had a colleague, when I got a DARPA grant, we got a big DARPA grant, and they said, okay, this is like the best thing. When you launch things, it's the best, and then it's all the hard work ahead, right? You got a lot of hard work ahead, and a lot of challenges to face, but just a tremendous amount of opportunities. So maybe I'll close off simply by again saying congratulations to all of you. It's just phenomenal what you're doing here, and I think we're all going to be watching very carefully. Thanks. Thank you.
So we have about 15 minutes for questions. I would like to open it up.
If I could, I actually have to leave in about, sorry, I have to leave in about 5 minutes because it turns out that I'm giving the opening keynote at 6E tomorrow because the opening keynote speaker has the flu. So I have to get to the airport. If, at the risk of being presumptuous, if there were any questions particularly for me, I'd love to hear those. Or not, that's fine too. That's my brother, he's a shill.
So if we succeed in dramatically expanding access to computer science in K-12, is that going to exacerbate the problem that others have talked about handling all the people who want to study computer science? Or does it connect with, is it one big picture of they shouldn't necessarily have to be computer science majors to use computer science and more joint degrees? How do you think about absorbing that?
Right. I mean, I think the answer is yes. It is going to exacerbate that problem, and it's a good problem to have. It's what Carla said before. It doesn't stop the people who were already going to be coming into the major, which is continuing to grow. It's not going to stop them from coming if more other kinds of people come. So that means that the growth is potentially going to be even larger. And I think, who was from Illinois? Rob. Rob, sorry. Who was talking about that, like, this has to happen. It has to happen, and so we have to deal with it and get out ahead of it. And it's a moral imperative that we do this in an equitable way. And I think partnering across disciplines is exactly the way that we can potentially do this. Because I know at my institution, there's pushback from the humanities worrying about the number of students who are majoring in computer science, and I don't want pushback from them. I want collaboration with them, because these students who we're training, a lot of them are going to go out and influence what happens in the humanities in the future, and we have to make sure we're working with them and educating students in a broad way and thinking about the implications of the computing that they're going to be doing.
Yes?
This is on online education. As far as the quality of online education, we get to a point in which we have good confidence that the assessment in terms of how well the education goes through as far as testing the student online, reaching the level of performance expected. Part one. Part two is, how do we convince corporation who is going to hire these people that the quality is there?
So the question has to do with online education and how can we be sure in computer science that the quality of the education and the value of the credential and the competency of the students going through it match those of campus education. I think we're well past that. A number of universities, top 10 ranked universities around the world and beyond, are routinely doing fully online learning for campus. Georgia Tech, for example, for its freshman computer science class, is giving its students a choice. Do the fully online class on edX from Georgia Tech or do the campus class? 60% of the students do that. And they get the same number on their transcript. Similarly, UT Austin has launched a computer science master's on edX. Georgia Tech has the computer science degree. They have an analytics degree on edX, a cybersecurity degree on edX from computer science and other departments, where the degree that the students get is identical to the campus degree. So if you just see a student running around have a master's, this diploma, this piece of paper from some of these universities, it is no different from the degree students get on campus. And so I think we're well past the point where we have to worry that the quality of the assessments, the quality of virtual proctoring and other techniques, we are well past those issues. From the corporate standpoint, I think the corporates are clamoring for more computer science graduates. And not only are they looking for graduates come out of these degrees, many of them are funding the students to go get the degrees. They're also clamoring for more micro-credentials. Many of the corporates are not able to send off their students for a master's. They want micro-credentials. And I think the challenge is there. How do we get the corporates to appreciate and recognize the newer micro-credentials as opposed to the older form large degrees? I think that remains a challenge. But as far as something's a degree, there's no difference in the piece of paper that they get, so the corporate does not know it's online or on campus today.
So, Dimitri, if I could add to
Of
that,
course.
Partly agree and partly disagree with my great colleague, and I got Regina in between to keep him from hitting me. So thank you, Regina.
And a chair.
She's a kickboxer.
I know, I'm worried. Look, I agree with Anant in terms of what you acquire from the classes you take online. I mean, at MIT, we talk about our online classes are MIT hard. They're not any different than the things we do. It's really important that that quality is there. And I really agree that that acquisition, which is why I think the MicroMasters work so well. The place where I think many of us, though, are still uncertain is, an undergraduate education is also about other things you learn in other places. It's on an athletic field, it's in a drama club, it's in a dorm room, or wherever. And that's the place where I think universities have to wrestle with what is it that is adding to the degree. And how to, for online, the credential is important, but that's about the knowledge. There's this other part of an undergraduate degree that I don't think we want to lose, and we got to think about that. And the reason I raise it is in online, I think there's a lot of progress, but the notion of forming communities to talk, You do that in a fraternity or a sorority or a dorm room if you're on a campus. Online, it's not yet quite the same experience, and we have to think about how to provide that.
I would like to continue the discussion asking all of you the following question. Oh, you wanted to add something to that?
Actually, I wanted to ask Eric a question then. Rather than turning the challenge around about saying, well, what about off-campus students? What about now the on-campus students, right? What about the challenge of providing them as a brick and mortar place where students are just there? What is it that we do that makes it better than consuming it online or sitting in a lecture? Or, you know, is it active learning? Is it you mentioned the co-curricular activities, but what about things that happen in the classroom, maybe a different classroom?
Yeah, so I mean, my reaction is I think in the classroom, some of it is mentoring, some of it is, again, is connections. I mean, I have to admit, when I teach a big class, I hate it when they're talking in class, so I'd rather they do it outside of it. But I think on campus, it's two things. One, it's being able to build the connections to have discussions afterwards that you get by being on campus. The other one, and I feel guilty saying it because I don't mean it to apply to me, but one of the advantages of doing it on campus, and one of the advantages of still having lectures, I mean, I'm mixed on this, is you get to see role models. I'm not one, but you get to see role models. You get to see mentors that you say, oh, that's cool. I mean, I think when it comes to diversity, that's an important part of who are those role models. And my experience is it's not the same as watching a video of somebody as actually being in the classroom going, wow, that's a Nobel laureate that's giving that lecture.
Yeah,
That's cool.
I think I agree with most of what Eric said, but I'll just give you a statement as to that today's generation of students is different. My daughter, a sophomore at MIT, her biggest superstars, her biggest role models are not people, I wish it was me, are not physical people. How many of you have heard of the Green brothers? These are spectacular YouTubers. They can put any professor, I mean, they're spectacular creators. She goes, you know, she ended up going for some major Green Brothers conference or something, just so she could be in a crowd of 20,000 people screaming, and it wasn't a rock star concert, it was educators. And so you can have people motivate you and inspire you online as much as in person. I think the physical reality, I think sometimes is not as good as the virtual reality.
So you knew there was going to be a discussion here, right? And so Anant and I are doing this really well. Thank you.
Regina, you had experience with both. You had flipped classrooms. What was your experience with using both media, both the online as well as the...
So I think that it actually depends how good is our experience in classrooms. One of the reasons that I stopped teaching 6036 is because we had 400 students in the class. So given this huge class, when you don't know your students and you really cannot have a discussion, I'm not sure that we're really delivering the goods. That's why, and also I kind of felt that I am teaching to everybody and nobody, because there were people who were bored in the classroom because they knew it, and there were people who really couldn't follow. So I think that the future is actually in combining the two and finding certain things that can be done online, especially teaching maybe very technical stuff where people need different, kind of personalized approaches, and then find a way to break up these big classes and really give the value to our students of having the discussions. And I was so happy. I just came teaching the new class, and it was really fun, and we had very extensive discussion. But I know that next year, when it's going to be instead of 90, it's going to be 250, we cannot have these discussions. So we really need, as MIT and other institutions where computer science grows, to think what is the most effective way of combining the technology so we do the best utilization of human resources. So maybe instead of me teaching, 26 or 27 lectures, maybe I will teach less lectures, less are recorded, but these lectures will be divided to subgroups where we really get to know our students.
Dimitri, really quick comment. I agree with Regina, and one of the disadvantages of a big lecture is that I don't know of any undergraduate who in front of 600 of their closest friends are going to say, "Professor, I didn't understand that." So if they miss something, there's no reset
But they
button.
do it when they are 60?
Sorry?
But they do it when they are 60? And
Well,
the graduates?
60, they'll get closer at 60.
Okay, yeah.
But my point about it is, one of the advantages about flipping the classroom and putting the lectures online is that a student will go back and re-listen to it. The other advantage, quick story, my older son and my wife took my MOOC. which
Oh,
was
boy.
really bad dinner discussion. Why the hell did you
Tell
do
us
it?
what grade they got?
Yes, I will separately. By the way, my wife is the head of the computer science department at Wellesley, an MIT PhD, so I don't know what the hell she was doing taking this class.
You inspired her, Eric.
The reason I want to tell you this story was because one of the things I discovered from both of them, which I think is interesting about putting the lectures online, they would, thanks to edX, they would mostly listen to the lecture at 1.5 speed, which they also thought was hilarious. You can do that until they got to a hard part of the class, and then they slowed down to 3/4 speed. The point is you give the student more control of what do I listen to, how quickly do I go through it, and I think the flipped classroom, that's an interesting opportunity. Then when you have the discussion, it's a discussion in a smaller group.
I mean, given that we don't have a lot of time, maybe I ask a very speculative question. So we have talked, and talk about Arizona using portions of the MIT Online and the other, and so forth. Let's consider 10 years from now. Georgia Tech had a College of Computing from 1990. Many other, MIT is doing it. Other places are doing it. It's going to be massively available. So do you see a future in which all this material, in the end of the day, do we need to have, it's like calculus. Does the nation need 3,000 courses on calculus? Similarly, does the nation need 3,000 courses in something and something? X plus computer science, for example, whatever the X is. Do we see a convergence that in the end, as far as undergraduate education is concerned, that we converge in an environment that maybe the vast majority of education is by few instructors online, and then we use other aspects that you mentioned. Very speculative, but something I wondered about it. I'm certain you have opinions, all of you. Maybe we go this way.
I'll put it differently.
Yeah?
My dream is, and I believe this is likely to happen, is that education will be like the slide I put up, will become like Legos, where 10, 20, 30 years from now, universities, rather than creating stovepipe programs for just their students, will create these modular programs, micro programs, micro masters, and so on. And they put them, for the campus students, they'll put them online, and various students in various universities around the world will create this networked digital economy where they'll borrow and micro programs from various places, micro masters or others at undergraduate level, and they'll compose customized degrees. And people want to be multidisciplinary. And this is already happening today. I'll give you a quick example. The IT university in Pakistan, new university, they have a computer science master's. They wanted to offer data science masters. They can't hire data scientists. They're all making too much money. So what they did was they had 6 courses, so 1-year masters, 6 courses taught by the computer science professors. edX has the data science micromasters from UC San Diego. And what they did was they incorporated 4 courses, the entire micromasters on edX completely online. And so the campus students pay campus tuition, and they do 6 courses on campus, 4 courses online from UC San Diego. They get a degree from IT University in Pakistan. I think in the future, I want you to think Legos, where when you get a degree, you will be asking people, where is the degree from? Can I see the provenance of each of your modules? Where did they come from? And I think people will be stitching things together, internships, programs. Some people take computer science. Eric is a spectacular teacher. Regina is a spectacular. I want to take those programs. And I want to do calculus from there. I want to learn Latin. I don't think MIT teaches Latin. Heck, I'd love to take Latin from Wellesley College. I think the future is going to be very exciting for the learner. Let's remember, it's all about the learners, not about us, the teachers.
Any other different views?
I think very. I'm sorry.
No,
James really wants to talk.
No.
You have the floor, James.
Really quickly, I agree a lot with Anant's vision, but I think one of the great opportunities is to combine 2 things. Somebody who's a great lecturer on some topic. Samuelson teaching economics. I would love to take a class from Paul. I never had a chance to do that. Or pick your favorite person. But then locally, to let the local instructor amplify that. So you watch the lecture from the really talented instructor. And on campus, then you have the dialogue. And that nicely blends that more interactive piece with somebody who's a great lecturer.
James?
I was going to say exactly what Eric just said.
sorry,
And
Jim.
actually, I was going to use Hennessy and Patterson as examples rather than Samuelson, since maybe we can all relate to that. But I think that it's absolutely the case, and I think of it actually more, I think of them as disembodied from universities, right? Think about really great textbook authors and people who think about how to thread common themes through through a series of ideas, and hopefully that'll resonate, and there'll be needs for multiple ways of approaching that. But I think the people who spend the time to think deeply about it, who have a particular style, who are good writers, because I still think we're going to have text, who are really good and inspirational speakers. I've never seen Feynman in physics, right? I mean, those, we now have the technology to do that. The question I was going to ask Regina is, if I wonder down the, not too far down the line that we're going to be embedding those kinds of materials with, let's say, smarter systems that have models of learners and try to understand better what learners are learning and not learning. And so, the Jill stuff that's going on at Georgia Tech right now is just basically simple question and answering. But once we have software that now has models of learning and understands how individuals are learning and looking how they're going through material, I think combining that is going to be great for online students. And then again, the challenge comes back, what are we going to do on brick and mortar campuses?
You've started to touch a little bit, but I want to bring that last discussion back to the perspective that James ended up with, which is the diversification and equity issue. Except for Anant, nobody has, and this somewhat is addressed at Eric's. I mean, I've been fortunate to have been attached to several universities and colleges with wonderful on-campus experiences. But the truth is that now 50% of nationally of our undergraduates are not traditional students. 50% are not 4 to 6 years and not finishing when they're something like 23 to 25. So how do all these different models address that part of the pathways, not pipeline issue? And one other little piece of that, I'm surprised I haven't heard anybody mention anywhere boot camps. I think they're mostly, I'm not an expert, but I assume they're mostly effective for coding and not really for the computational thinking. But how does that stuff all fit in?
Anybody volunteering?
Well,
James?
I might start off by saying, just in terms of student backgrounds, I heard Eric say that the online courses are MIT hard, right? And honestly, not everybody can take MIT hard courses, right? And if you're going to teach MIT hard courses, and that's going to be the folks that you address, great, right? That's really important. So there is need for lots of other institutions to be addressing those kinds of things. I mean, exactly the diversity issue that you brought on. So I don't see that it's just going to be some number that we can count on a couple of hands and feet, that this is going to be the number of professors and numbers of universities that are going to thrive, because we do have such a diverse population. But then it's up to the individual brick and mortar campuses to now define how they're going to do that and what who their students are going to be.
And I would just add, I didn't mean to come across as arrogant, but MIT knows how to teach MIT kinds of people. I know how to teach MIT students. I'm not skilled at teaching K-12 students. We need partners to create parts of that pipeline. But I'd simply give you a number, and my apologies for using it, but I've had 1.2 million people show up for my class. I occasionally get stopped in airports, which is a really weird experience. But of that, and Anant can probably, of that 1.2 million, the youngest student that successfully completed my class, I think, was 10. Wow. And the oldest was in his 90s. And so there's a whole range of learners that really want to do this. I'm not perfect for everybody, but we need partners to think about filling in the other pieces of this.
Wall Street talks about how many millions you have. As educators, when we talk about how many millions we have.
Different millions. I would love to go for further, but given that there are other events, I would like to end the discussion right now. I would like to thank our panelists, and there is continuation later.